Today I will introduce our recent work on robust top K multiclass SVM for visual category recognition. This is a joint work with my PhD supervisor, Professor Yi Yang, and my friend, Dr. Yaoliang Yu from University of Waterloo. I'm Xiaojun from CMU. This talk will introduce 4 parts. The first part is the introduction of multiclass SVM. And after that, we will give some preliminary work on multiclass SVM. Then we will introduce our proposed robust top K multiclass SVM. Finally, we will conduct some experiments to evaluate the proposed method. The first is the background of multiclass SVM. Multiclass classification is a fundamental task in the field of machine learning and computer vision. There are many real-world applications for multiclass classifications, including object recognition, image segmentation, and scene classification. A multiclass classification problem is very difficult because the classifier needs to distinguish an object from a large number of categories. When the number of visual categories becomes very large, the visual recognition problem becomes extremely challenging in the presence of similar or overlapping classes. In the next slide, we will show an example of the similar or overlapping classes. This is some video examples from FCVID dataset. This is a dataset from Fudan University. From this, we can see that figure A is a class of beach, and figure B is a class of mountain, and figure 3 is wedding ceremony, whereas figure D is wedding dance. We can see that figure A and figure B have some overlapping, and the objects in figure C or the class in figure C and figure D are similar. So it may be difficult for human being to distinguish a wedding ceremony video from a wedding dance video. So it is not reasonable for us to ask a machine to distinguish exactly the video of wedding ceremony from the video of wedding dance. So for such challenging problems, it makes sense to allow the learning algorithm to present K predictions altogether to the user, as long as the true category is among the top K predictions. This assumption also aligns with many real-world applications, such as ad display or search engine. When you search something using Google or Yahoo, you always expect your results are within the top 10 or top 20 results. So recently, some researchers proposed the top K multiclass SVM as a direct method to optimize for the top K performance. It strictly generalizes the multiclass SVM based on a tight convex upper bound of the top K error. So now comes to the contributions of this paper. Contribution 1, we propose a very generic, robust multiclass SVM formulation. Its goal is to directly minimize a weighted and truncated combination of the ordered prediction scores. And contribution 2 is we also show the algorithm can include many previous multiclass SVM as special cases. Contribution 3 is based on the decomposition lemma, we propose an efficient algorithm that allows to incorporating many popular regularizers like L2 long regularizer or L1 long regularizer. So now is some preliminary work. The first is traditional multiclass SVM. This is very simple. Given training sample, xi is the data, and yi is a class label. The multiclass SVM aims at to minimize the following regularized empirical risk. The first term is a loss function, and the second is a regularization. And the loss on the ith chain example is given by equation 2. So to predict the label of a test point x, we use a max rule. Max rule is formulated as this formulation. So ties can be broken in any consistent way. So from this prediction, it is clear that the prediction is correct if the scores satisfy this equation. So accordingly, the multiclass loss in equation 2 is designed to enjoy this property. So this is a traditional multiclass SVM. And recently, some researchers considered the following set prediction rule. So y is the coordinate of y is k. So if we put the right result is within the top k prediction results, we are happy with this prediction result. So namely, we present the k labels whose scores are among the top k, and the prediction is considered correct if the score satisfies the equation, where we use this term to denote the k's largest entry of the vector A, and the matrix to remove the yth row of W. Accordingly, the researchers modified the multiclass SVM loss equations as follows. And Ej is a j's canonical basis vector, and y is the all ones vector. So we have this equation. And the top k loss in equation 8 is unfortunately non-convex. So instead, Lapin proposed the following convex upper bound up to a scaling of factor k, and they finally arrive at this optimization problem. So the major limitation of this convex equation and also the original non-convex top k loss equation is their sensitivity to abnormal observations, for example, outliers. This is mostly due to the unboundedness of the corresponding losses. So to overcome this limitation, we propose the following truncated loss that extends the multi-category loss. This is our proposed loss function, where we use the following abbreviation for the scores. This is the score formulation. And we can see that it is clear that our formulation includes many previous multiclass SVM as special cases. So if tau equals infinity, alpha 1 equals 1, alpha 2 through to alpha c equals 0, then we recover the traditional multiclass SVM. And if tau equals infinity, alpha k equals 1, alpha 1 through to alpha k minus 1 equals alpha k plus 1 through to alpha c equals 0, then we recover the non-convex top k multiclass SVM. This is only the case alpha equals 1. So if tau equals infinity, alpha 1 to alpha k equals 1, and alpha k plus 1 through to alpha c equals 0, then we recover the convex version of Lapin. And if tau equals 2, we have alpha 1 equals 1, then we recover a similar formulation. This is another reference. So we can combine the robust multiclass loss equation with a regularization function to promote structure, resulting in the composite minimization problem. The minimization problem is formulated in equation 14, where we can choose, for instance, the L2 norm regularization for generalization or L1 norm for sparsity. In general, our robust loss in equation 12 is not convex due to the truncation by tau and the weight of alpha. However, if tau equals infinity and alpha 1 larger than alpha 2 and larger than alpha c is monotonically decreasing, such as the multiclass SVM and the convex version, then the formulation equation 14 becomes a convex minimization problem. And to solve this problem, we rewrite this optimization problem into a differentiate complex convex algorithms. So this is a optimization algorithm for this problem. So you can see that there are only 25 lines of code. So it's very simple and quick and fast. So we conduct extensive experiments on for large-scale datasets. These are for real-world video datasets. And we compared with some state-of-the-art multiclass SVM algorithms. And for all the compared algorithms, we cross-validate the regularization parameter lambda in the range in this range, and the visual splits are used for all the compared algorithms. For the proposed algorithm, we also cross-validate the hyperparameter tau. So this is the experiment results of visual recognition, and this is top K accuracy is used as the evaluation metric, and this is top 1 multiclass SVM and top 2 multiclass SVM. And from the results, we can see that the proposed robust top K SVM always outperform the other compared baselines. And this we also do some robustness evaluation experiments, and these are the experiment results on the 4 datasets. We can see that if the outliers, if we got more outliers, we can get more advantages baseline algorithms. The similar observations are made on the 4 datasets. And we also do some sensitivity analysis. We tune the parameters. And we can see that the best performance is always obtained when tau is in the range of 1 to 10. So similar observations are on the 4 datasets. So this is observation. This is sensitivity analysis with right to lambda, and we can see that we can see that the best performance are obtained in similar scenarios. That is always -2 to -1, this range. So that's all.